Howdy everyone. Today I'm going to run over a tutorial here in the Circuit of Knowledge on my website, and this is under probability theory. Let's go, and here we have the inverse transform sampling method for generating the maximum of uniform random vector. Okay, so the idea is this. Sometimes, a lot of times in engineering, we have to do simulations, like for example in radar. In radar we have a vector of values and we seek the maximum, sometimes the minimum or any other statistic over this vector of values. So when we simulate that, the naive way of doing that is to simulate a random vector and then let's say uniformly distributed, and then search for the maximum, and then do it again and again and again until we have a vector, a big vector of maximum values. And then we can plot its histogram, for example, and extract information about its distribution. Okay? This method is highly time consuming because we search for the maximum and we generate a lot of vectors. Let's say 1,000 vectors. We generate 1,000 vectors of, let's say, 1,000 entries for having the distribution of 1,000 maximum values. So this is not very efficient. How can we circumvent that? There is this method or algorithm called inverse transform sampling, ITS, in probability. I teach it in my course, and it says that for any arbitrary CDF, cumulative distribution function, that upholds some criteria, so we assume something about it, but we're not going to cover it in this simple yet insightful demo. We can inverse this CDF if we have it, and then plug into this function run uniformly distributed random variables between 0 and 1, and what this inverse function will spit out is a random variable that is distributed according to the CDF that we want. Okay? So for example, the CDF of the maximum of n uniformly distributed random variables is, after some calculation, we can see that it's x to the n for x between 0 and 1, 0 for x below 0, and 1 for x greater than 1. Okay? But we are interested in this x to the n. Okay, we are going to invert it, and then we have u to the power of 1 over n. Now if we generate 1,000 u's like this from a uniformly distributed random number generator that we have in Python, we generate thousands of these, then we will have thousands of these x's, which follows the distribution f sub x. Okay, that's another distribution of the maximum, and we can see it here. I just return u to the power of 1 over n. I generate 1,000 of these, and we can see the distribution here, the histogram. Okay, we can see that it has a tail that goes to 0, from 1 to 0, but the mode is tending to 1, which is making sense because it's the maximum that we are measuring here. Okay, now we can do a runtime comparison between this method right here and the naive method, which is to draw a uniform random vector, let's say of size 1,000, and then search for the maximum and return it 10,000 times. And we can see that the slower one is 158 millisecond, and the fastest one, which is our method, the ITS method, is beyond the resolution of what I'm measuring in this program, this code. It's probably microseconds. And we compare the histograms of both methods. So a lot of times in engineering we wish to accelerate Monte Carlo simulations, and this is a very good way to do it. Thank you for watching. Stay tuned for the next video, and also don't forget to subscribe to the Circuit of Knowledge section of my website. There are, I think, right now about 30 plus or 40 plus tutorials such as this. We can see that here. The topics are AI and machine learning, probability theory, radar theory, control systems engineering, and paper summaries. In AI and machine learning we have a few, and it's growing very fast. In probability theory we will have quite a few, and so on and so forth. So subscribe there and like this video, subscribe to my channel if it brought you value. Thank you for listening and have a good day. Bye bye.